Good day, everyone, and we meet yet again. And today I want to just look at circuits with switches in them. So we've covered electricity quite extensively. If you haven't watched those videos, just make sure that you get yourself up to date. And we've covered quite a bit on circuits. But today I just want to add on to that circuits with switches onto them. So if you haven't subscribed to our channel, welcome, and you're more than welcome to become part of the family. And by the way, if should you have any questions, you're more than welcome to just put the comments there, and please hit that thumbs up if you do like our lesson. So let's get into it very quickly. Right, so first of all, let's talk about the function of a switch in a circuit. All right, we all interact with switches. We do act with, we do encounter switches daily. But what exactly does a switch actually look like, or what does it do? So if you think about it, a switch, basically all it simply does is that it's a device that allows or disallows current, okay, to flow through. Now, if you look at this structure, for instance, this is a symbol of an open switch. Now, I want you to please note, when a switch is open, okay, so this would be an open switch. So we say that when the switch is open, first of all, we need to be to remember that what it simply means is that we have infinite resistance, okay? So if you think about it, so when you've got an open switch, you've got infinite resistance, and as a result, because you've got such a big resistance, right? So because you've got such a big resistance, right, it disallows current from flowing. So as a result, that is why in an open switch, current won't be able to flow. However, if obviously we close the switch, okay, so you just connect those two up to there. And by the way, we are talking about ideal switches, okay? Sometimes in real life, of course, these guys don't act as we expect, but these are ideal switches. So in an ideal switch, right, if I close a switch, so this is a closed switch, what does it do? Now we begin to have zero resistance, okay? Please keep that in mind. So a closed switch has got zero resistance, so it does not resist current at all. So as a result, what begins to happen, right? It will obviously begin to allow current to flow, right? So a maximum amount of current will be able to flow. So we said in an open switch, infinite resistance. So in this case, no current flows. All right. And I want us to look at an application just now. Okay, so no current flows. And this one, we've got a closed switch, so we know that it will allow a maximum amount of current. So maximum current flows there. Right. Now keep this in mind, ladies and gents. Now, quickly, I want to just move to a switch that is particularly connected such that you are not able to have a current flowing in your external circuit. So suppose that we've got a circuit, okay, and we know that we are given an EMF and we've got an internal resistance. Now, please, I want you to listen carefully, ladies and gents. So suppose I've got an external switch there. So there's a switch in my circuit, and there's my resistance. Okay, so let's call it resistor R, and there's my emitter there, and all right, so that's emitter A. So ladies and gents, if I put a voltmeter onto this circuit, remember, a voltmeter, all that it simply does is that it measures the potential difference, right, between 2 points. Now, please, I want you to listen carefully. So if I connect a voltmeter here, and this switch is open, all right, so what will simply happen is that this voltmeter will simply read off over this battery the value of the EMF. Please keep that in mind. Why? Because remember, we'll only have the internal resistance acting as an internal resistance or resisting, right, if there is a flow of current. So the moment we do not have current that is flowing, we are not going to have or to experience, in this case, internal resistance. Okay, so as a result, when this switch is open, right, and I measure across the battery, what I will simply get, the value V that is measured there will be the value of the EMF. So it means that my external voltage, in a sense, right, will be equal to the EMF value, right? Now, the moment that I begin to close the switch, okay, suppose here we are closing the switch, of course now current begins to flow into your external circuit, okay? So what happens is that you'll see a voltage drop, okay? You'll see the voltage there beginning to be a different value. So V external will simply change. It will be less than, in fact, let me say V external will be less than the EMF. Why? Because some of that voltage is actually lost in that internal resistance, due to the internal resistance. So I want you to keep that in mind, right? So the moment that I close the switch, in this case, it means that my V external will be less than the EMF. And as a result, remember, your EMF does not change. That's your maximum energy, all right, per unit coulomb of charge, right, across the battery. But in this case, it means that now the voltage to your external circuit now begins to change. And so what I want us to do very quickly is to take an application of what I'm saying and to show you how we are going to apply these things, these switches. But before I just get into that quickly, suppose what were to happen if I were to have, let's say, just put a wire across here. Okay, so let's say we put a wire there. We've got a switch and that switch is open. Okay, right. So if that switch is open, nothing would happen, right? So you'd have your current flowing, all right? And obviously, because current cannot flow in an open switch because of infinite resistance, right, all your current will flow through resistor R, right? But now, the moment I close that switch, and I want to make you aware of this, remember that a switch ideally has got zero resistance, okay? So what will begin to happen there is that now all of a sudden your current says, so which path should I take between this one and that one? And now, remember we said when you connect in parallel, right? More current goes where there's less resistance. Now think about it. There's zero resistance over here. So guess what? All your current will begin to go through this wire over here because there is zero resistance. So in this case, it means that this resistor here will not function anymore, or in this case we say that we call this a short circuit. Okay, so by putting a wire across a resistor or any device, what you are doing is that you are short circuiting it. All right, it means that the current will just go over it, okay, around it rather than going over it. Okay, so as a result, we call this a short circuit. Okay, so in this case, that is how we are going to apply switches. Now quickly, I want us to take an example because it's always important that when I teach a concept, I show you also how it would be applied. Okay, and I'll show you how to even answer past exam questions. Let's take that in a while. Right, so I'm taking the March-April paper. This was supposed to be written by the senior certificate for the senior certificate examination as sort of a prelim, but the main thing is that it's a question paper that actually allows us to apply what I've just shown you. I hope you can see it quite clearly there. Right, now they give us in this diagram, right? They say in the diagram below, a battery of with an EMF of 6 volts and an internal resistance of 2 ohms, right, is connected to 3 resistors P, Q, and R. Okay, so there's your 3 resistors P, Q, and R. Okay, they say voltmeter is connected across the battery and the ammeter has negligible resistance. Okay, right. So now we said all the time when we're going to look at a circuit, we're going to first analyze, isn't it? Okay, so look at this. We know we've got a voltmeter that's measuring there, but note when there's current flowing in the external circuit, there'll be a difference between the value of our EMF and the value of our external voltage. Okay, please keep that in mind, that in this case the EMF, this value here should be less than the value of the EMF, but we'll talk about that as we go along. Right, so what's going to happen here? I'm going to have current flowing outside the circuit, and obviously current is going to divide. These two resistors are in parallel. That switch there is closed, right? So it means that current will be able to flow through the 15 ohm resistor, okay? And as a result, also able to flow through the 10 ohm resistor. Okay, the total current flows through there, the ammeter, the total current also flows through the 10 ohm resistor. As I said, ladies and gents, if you haven't yet watched my other videos on circuits, please do so, because they will help you to actually know how to navigate your way through circuits. Right, now let's have a look at the first question. Right, they said calculate the ammeter reading when switch S is closed. Okay, so we've got a closed switch, as they said. Okay, so now we want to find out what is our ammeter reading. Okay, right, so now we know in this case we can use, we always start with what we are given, right? So we can use the value, or rather the equation for EMF. We can say, look, we can say E is equals to I into R plus small r, right? Now notice, do we have EMF? Absolutely. We want to find out the value of the current. That's what we want to find. And in this case, is it possible for us to get the external resistance? Absolutely. And we are also given the internal resistance. Okay, so definitely this is the way to go. Okay, so I'm just going to go through that quickly. So first of all, because we want current, let's try to find out what's the value of our external resistance. Okay, so we know those two resistors are in parallel, all right, and the combination of them should be in series with that 10 ohm resistor. So let's find out the parallel combination. So I'm going to just say R parallel. Okay, so I'm just going to say R1 times R2 divided by R1 plus R2. If you don't know where this comes from, by the way, you could also have just simply said 1 over R parallel is equals to 1 over R1 plus 1 over R2. And in this case, all that we simply did was just to manipulate that, and you end up with that. It's a much easier or much simpler format for you to calculate the external resistance. But just to caution you, please remember this only works when you've got only two resistors in parallel. Okay, so please don't try to use it when there's three. There is another one that accommodates more resistors, but it just gets complicated from there. Right, so now what we're simply going to do is just to say 10 multiplied by 15. Okay, those are the two resistors there, divided by 10 plus 15. Okay, and that should give us a value of, end up with the value of 6 ohms. Okay, and by the way, I did caution you that whenever you've got two resistors in parallel, your effective resistance, your effective parallel resistance should be smaller than the smallest resistor. And in this case, 6 is definitely smaller than our smallest resistor in parallel, which is 10. So definitely this tells us that we are on the right track. Now, all we've simply done now, keep in mind, what we've simply done is that we've made those two resistors into one, okay, and that value is 6 ohms, and there's our ammeter there, and there's our 10 ohm resistor. over there. And of course, it's our batteries and so on and so forth. Internal resistance. Okay, so now note once again, so the total current flows through the 6 ohm and it flows through the 10. So in this case, it means that our external resistance, now we can say, okay, we know that our external will be equals to the 6 ohm resistor. Okay, these are going to be in series, so it's going to be 6 plus 10, and it means that we've got 16 ohms. Now, can we now calculate the current? Absolutely, right? So we are now going to say, okay, we know that EMF, okay, remember we said EMF is equals to I into R plus small r. Remember we said E here, that's the EMF. They said it's 6 volts. We want the current, okay, that's R external, remember, okay. And if you don't know if you don't know that, it means you haven't watched our previous videos on circuits, right? So this means that this is R external, so that's 16 plus plus the internal resistance, which in this case was given as 2 ohms. Okay, all right, so let's calculate our current value quickly. Okay, and we simply get a value of 0.33. Okay, so 16 plus 2, that would give you 18. So you divide both sides by 18, that should give you 0.33 amperes. And that's how we get our first value, what we're given there, when switch S is closed. Okay, now quickly, ladies and gents, I just want to show you. Okay, I'm just going to move this over to this side. I hope that you are able to catch everything that I've written there. Okay, I just want to use the other side for your benefit. Okay, right now, so they say to you now, the switch S is now open. Now, ladies and gents, what I want to quickly do, okay, let's see what's going to happen when we open switch S. Notice the moment switch S is open, right, note that switch S is not going to affect your entire circuit. Okay, so the moment switch S is open, it's only going to affect your 15 ohm resistor, right? So it means that this 15 ohm resistor will be as good as non-existent, okay? Because now you've got infinite resistance here, no current is flowing, so it means that my current will now begin to flow. Okay, it will go, all the total current will go through the 10 ohm resistor, okay, and all the total current obviously will go through the 10 ohm resistor. Of course, this does affect your circuit. It does affect the value of your current, okay, your current value, and it does also affect the value of your external voltage. Okay, so V external also gets affected. So I want us to look at that in quickly. They say, will the ammeter reading in question 9.2.1a increase, decrease, or remain the same? Now, please, I want you to stay with me and just quickly listen. So the first thing that you're going to do every time they ask these type of questions, right? The first thing that I always want you to look at is, how will your external resistance be affected? So first of all, even if they didn't ask you about R external, because how R external behaves or how it's affected will ultimately affect how the rest of your circuit is affected, meaning it will affect your external your external voltage as well as the value of your current. Okay, now let's check how is R external going to be affected. Now please remember, ladies and gents, every time that you disconnect a resistor in parallel, all right, your R external will always increase. Look at this. What was my previous value for R external? We got a value of 16 ohms. You remember that? Okay. But look at it now. Now that your switch has been open, it means that I've disconnected this 15 ohm resistor here. So it means that my total current goes through the 10 and it goes through the 10 ohm, the other 10 ohm resistor. So in essence, it means the same current that flows through the 10 ohm resistor will also flow through the other 10 ohm resistor. So the same current that flows through resistor P will also flow through resistor Q. Right? So what does it mean about these two resistors? It means they will now be in series with each other. So meaning, if I look at R external, of course they didn't ask us to calculate this, I'm just showing you. So it means that my R external now will actually be two resistors in series and each of them 10 ohms. So it means that my R external will now be 20 ohms. I'm sure you can see it, ladies and gents. It moved from 16 to 20 ohms, so it means that my R external has increased. So please always keep that in mind. So once they start asking you those increase decrease questions, you must always look at how R external is affected. Now let me show you why. So according to Ohm's law, current is directly proportional to the potential difference, provided that temperature remains constant. So the moment that R external increases, okay, look at that. What's the relationship between current and R external? It means that my current will simply decrease. They are inversely proportional to each other, right? So the moment that I increase R external, it means that my current will decrease. So what's our answer for this? It means that the current that we calculated would decrease, right? And they say give a reason for your answer, all right? And that is your reason, that an increase in the external, or rather, when we open the switch, our external increases, and as a result, it means that our current will decrease. Okay, right. Now quickly, let's look at the next question. And they like these kind of questions, and I'm going to show you, ladies and gents. Probably this one is a bit cumbersome to answer, but I'll show you step by step how to answer that. They say, how will the voltmeter reading now compare with the voltmeter reading when the switch was closed? So it means, how will your external voltage be affected? Now, I want you to keep in mind two things that remain constant in a circuit. Of course, if I don't add any more batteries or whatever, two things that should always remain constant, okay, will be the EMF of the cell, all right, as well as the internal resistance, okay. Of course, we know this is not factually accurate when it comes to real circuits, but remember, we are just talking about ideal resistors here, right? So two things that would remain the same, that would be your EMF as well as your internal resistance, right? Now, we want to know, how will V external be affected, okay? So what we are simply going to do is that we are going to say, okay, but when we look at V external, okay, first of all, we've just found out that current has decreased, isn't it? So now if you look at, let's take this formula, IR plus small r. Now remember, small r stays the same, okay? We've just discovered that current has decreased. Can you see that? Okay, right. Now, in this case, let me just write it in another format, all right? So I'm just going to say, okay, but we know that I times R is V external, okay, plus, let's say, V internal or V loss, okay, right. So our internal resistance stays the same, but our current has decreased, okay. So what is that going to do? So remember, V internal, that's going to be current multiplied by R internal, okay. So current has decreased, this guy remains the same, so as a result, what's going to happen to our V internal? It's going to decrease, okay. So note that V internal has decreased. Remember, we're trying to find out what has happened to V external. So remember, because EMF stays the same and this guy has decreased, now V external is obliged to increase. Okay, now let me show you this in number form. Remember, this guy was, and I'm just going to thumb suck numbers. Okay, remember EMF stays the same, so EMF would stay as 6. Now in this case, I've got a sum of two things, all right, which is V external and V internal. I've just established my V internal. Let's say initially, okay, our V external was 4, and our V internal obviously would have to be 2. Okay, remember, I'm thumb sucking this value. Remember, right hand side has to be left hand side has to be equal to right. Now all of a sudden we've just found out that V internal has decreased. Remember, this value has to still remain the same, 6, right? So if this value decreases, let's say now it becomes 1.5 volts, okay, what should happen to this value? Okay, obviously now it can no longer remain as 4. Now it has to be 4.5. So which means that V external has to now increase because the V internal has decreased. Okay, I know that sounds like a mouthful. Okay, right, so they said will it increase, decrease, or remain the same? So it means that V external will actually increase. So V external will say it increases. Okay, right, and obviously they want us to explain our answer to 9.2.3, right? And how I always try to answer that is actually using exactly the equations that we had. We've just found out that current has decreased, okay, but because EMF remains constant, right, V internal will decrease, and as a result V external will increase. Okay, exactly in that order. All right, so we said an increase in R external will decrease the current, right? But because EMF and internal resistance remain constant, V internal will decrease, and as a result it means that V external will increase. Okay, now ladies and gents, I know that that may sound like a mouthful. Just keep in mind, when you want to know whether V external increases or decreases, a quick rule of thumb simply says, whatever happens to your R external, all right, when we've got EMF, right, whatever happens to your R external, okay, V external will follow. Meaning, if R external increases, like in this case, you remember that R external increased, right, from 16 to 20. So it simply means that V external will also increase. Okay, right. So that is how we'll answer questions whereby we've got switches. Maybe let me just take another question just to show you quickly. Right, I want to take a very quick question, and you can look at it on how we apply that. Right, so let's take the November 2019 paper just to show you quickly how to apply that. Okay, so what I like about this question is that it just brings to life what I've actually been trying to illustrate to you in terms of circuits, right? They say in the circuit diagram below, okay, so we've got resistor R, which has a resistance of 5.6 ohms, which is connected together with a switch, an emitter of a high resistance, with a high resistance voltmeter to a battery with an unknown internal resistance. So there it is there, you've got that simple setup. So all that statement is just simply trying to show you what you actually have in that circuit there. Now they say the graph below, which is this graph over here, shows the potential difference across the terminals of the battery as a function of time. Now I want you to please note, okay, they said at time t1 the switch is closed. All right, now please note, so what happened, they had a voltmeter over there, right, and in this case the circuit, or rather the switch, was open all that time. Now the moment they closed the switch at T1, which is what we are told over there, the moment they closed the switch, okay, that voltmeter value or that voltage value dropped from 13 to 10.5. But why is that? Because of what I said to you earlier on, right? So what simply happened here is that there was no current flowing, so the voltmeter reading was actually giving us the value of the EMF. So in essence, in this question, what they are simply telling us is that the EMF of the circuit is actually 13 volts. Okay, so as a result, so now we know the value of the EMF. Okay, so we're going to calculate all the other things. Okay, so I'm not going to finish all the question up, but I'm just going to give you the important things, right? Right, so we know that the EMF value is 13 volts. We know that the V external now, so it means this value here, 10.5, is the value of the external voltage. Okay, please keep that in mind. Okay. Right, so they say define the term EMF of the battery. So remember, we say that EMF is the maximum energy per coulomb of charge across the terminals of the battery, okay, or across the terminals of a cell, right? So it's the total, or it's the maximum amount of energy per coulomb of charge. All right, that's the EMF. That's the definition of it. They say write down the value of the EMF of the battery. Do you see? They didn't say calculate. They just simply said write it down. So already we know that our EMF value is simply going to be 13 volts because they wanted you to actually know that that value that's given there is the EMF. And then secondly, they say when the switch is closed, now they close the switch. Okay, so now we know that the V external value is going to be 10.5. Okay, they say calculate the resistance, the current through resistor R. Okay, so now we have a normal circuit. We've got only one resistor, external resistor there. So in this case, we're simply going to say, okay, we want the current. We know V external, we know R external. So all we simply do is just to apply Ohm's law. I is equals to V over R. Okay, remember we said voltage with corresponding resistance, right? So the voltage across this resistor, okay, is that 10.5 there. Okay, 10.5 divided by the R external, okay, the external resistance, and we'll simply get our value there. Okay, so that's 10.5 divided by 5.6, and we get 1.875. Okay, if you wanted to convert that to 1.88, that's still okay, particularly if the examiner said you can use what do they call it, 2 decimal places, right? All right, and then the next question, they say the power dissipated in resistor R. Okay, now what do I know about resistor R? I know the current through it, I know the voltage. So you can use any of the 3 equations as I did show you the other time. So that's P is equals to V times I. I know the voltage across resistor R. I know the current through it. Or you could have used P is equals to I squared R. Okay, you should get the same answer for all of them. So okay, let's take this one, the second one. So that's 1.875 squared multiplied by the resistance is 5.6. Okay, so 1.875, okay, squared. All right, multiplied by 5.6. Okay, I get a value there which is 19. Okay, I'll just say 19.69. Okay, remember, sorry, power is measured in watts. Okay, by the way, nothing wrong if you said P, that's V times I, so you would have said 10.5. Okay, which is our voltage value there, multiplied by that current 1.875. Okay, and you get exactly the same answer, 19.69 watts. Okay, And then quickly, just to show you, ladies and gents, then they said to you calculate the internal resistance of the battery. Okay, so now that you know the external resistance, okay, uh, um, not just the external resistance, but you also know everything else about the circuit, you can use E is equals to I into R plus small r. Remember, we said here we use the total current, here we use the external resistance. Okay, so the EMF, we said that's 13. Okay, current, we've said that's 1.875 or 1.88 if you want to. Okay, R external, we're given at 5.6, and obviously we are now going to calculate our internal resistance, right? And of course you're going to do all your mathematical gymnastics. Okay, that's divided by 1.875. Okay, and you subtract there 5.6. all right, and I get a value of 1.33 ohms. Okay, you can verify it. Okay, and you can just hit me with a comment there if that value is correct. Okay, so that is how we navigate through circuits. I just wanted to illustrate that to you, ladies and gents. And by the way, we're still going to do some revision going towards our prelims, and just look out for more videos that are coming up on that. But otherwise, I just want to leave this question over here, and thank you once again for watching. It's been great having you with me. All right, and I'll see you next time. And please don't forget to subscribe if you haven't, okay? And just hit a thumbs up if you really like the lesson. Otherwise, it's bye-bye from me to you for now. Sharp, sharp.